In this video, we're going to be discussing arc length of a curve. We'll discuss arc length both as a function of x and as a function of y. There are all kinds of applications in Calculus 2, 3, and engineering where the ability to figure out how long a curved path is important. This is essentially what arc length is. It's the length of a curved path. To calculate arc length, which we studied already in both parametric and polar, we need to have a stronger requirement on the functions we study. In particular, we need these functions to have what are called smooth graphs. Smooth graphs are very important in Calculus 3 as well. Let's take a look at what a smooth graph is. A smooth graph is one in which the first derivatives are continuous functions. In Calculus 3, we'll represent functions in vector parametric form, and in that form the derivative also cannot be the zero vector. Smooth basically means that the first derivatives exist and the first derivatives are continuous. Now, because we have the first derivatives being continuous, that means we have to have a derivative, but it also means that we don't have any tangent lines where the slope goes vertical, or no corners and no cusps. Because differentiability implies continuity, this means that we know the function itself has to be continuous. If differentiable, then continuous. The reverse is not true. We do have many curves that are continuous but aren't differentiable. For example, the absolute value function is continuous, can be drawn without picking up the pencil, but it's not differentiable at the corner at the origin. In this case, as long as we have a smooth curve, that means that we do have differentiability, and that means we have to have continuity, which means we have no holes, no displaced points, no jumps, and no infinite asymptotes over that interval either. In addition, since the first derivative itself is continuous, the first derivative's graph can't have holes, displaced points, jumps, or infinite asymptotes either. So how do we take a curve, such as the curve that you see here, or the curve that you see over here, and compute the length of that curve? Since it's not straight, you can't exactly take a tape measure and run it along the edge. But in essence, that's sort of what we do. We cut the curve up into smaller pieces, and then over each small piece, we approximate the length using the Pythagorean identity. Let's take a look now at a smaller shape. If we required the curve to be smooth and we make our cut small enough, then they become more and more linear as we make the cut shorter. That's because each individual piece has to be curved smoothly. It can't have corners or cusps. And if we do, then as we make the cut shorter and shorter and shorter and shorter, the small little line segments in between become straighter and straighter and straighter, and they become more and more like line segments. When we're looking at it, let's look at how we can use the Pythagorean theorem to approximate the length of the curved section. So for example, going between x naught here and x1, we have the function value f of x naught, which is this here, and f of x1, which is this here. We want to find the length of this curved section in the darker blue, and we approximate it with this straight line segment in the orange-red color labeled C. We do this by using the Pythagorean theorem. You can see at the picture on the right that what we do is we take the difference in the x values and the difference in the y values, which of course are the function values at the point, and we apply the Pythagorean theorem to them. This will give us the length of the orange-red color, which is the hypotenuse of that right triangle. Once we do this, if we make the cut small enough, then you can see that they become straighter and straighter as we become closer and closer to the curve, until the hypotenuse of the triangle is almost exactly on the curve itself. It can't be exactly the curve because the curve is arced. The curve is, well, it's curved, it's not straight. But as we make the cut smaller and smaller, it gets closer and closer to that value. That means that we are using the approximation from the Pythagorean theorem that C is equal to the square root of the change in the x value squared plus the change in the y value squared. If we use a regular partition, that means that we're cutting up our axis so that all of the distances between the x values are exactly the same. A regular partition then means that all the delta x's become the same, and the only thing that's changing in the radical will be the delta y's, and those will depend on the function values at the two endpoints of each little cut or each little line segment. Now we apply an algebraic trick to get the expression for slope, delta y sub I divided by delta x. We're going to multiply by delta x divided by itself, which of course is the number 1. So we start with the Pythagorean theorem expression for c, which is the hypotenuse of that right triangle. We multiply it, numerator and denominator, by delta x, which of course is just the number 1. We'll leave the numerator delta x on the outside, but we slide the denominator delta x into the radical by squaring it. Once we do that, we'll distribute it over the two terms that were originally underneath the radical. Since we've used a regular partition, all of our delta x's are the same, so we get delta x squared divided by delta x squared, which of course is the number 1. Then we have delta y sub I, the value or the change in the y values on the ith cut, divided by delta x squared. This would be the slope of that ith sub-rectangle or ith sub-triangle. And this gives us our formula right here. Since we have a function that's both continuous and differentiable over the interval by our requirement that it be smooth, then we can use the mean value theorem. Remember what the mean value theorem says. If it is continuous on the open and differentiable on the closed, or rather backwards, if it's continuous on the closed and differentiable on the open, then we can use the mean value theorem to say there must be some point in there that has the slope of that tangent line. The tangent line, of course, is the one that's connecting the two. It's the secant line. And so there must be some point that we can call x sub I star where we have the slope of that secant line that's connecting, that's cutting across. Let's look back at our picture where it was blown up a little bit better. In other words, somewhere between x sub I minus 1 and x sub I, there is a point where the slope of the tangent line is equal to the slope of the secant line, where the secant line connects these 2 points. In fact, you can almost take something across and figure that it's probably right about in here, where there's an x value where the slope of the tangent line is equal to the slope of that line. That's guaranteed by the mean value theorem. Since we're guaranteed that there is this point where the slope of the tangent line is equal to the slope of the secant line, we can replace the delta y sub I divided by delta x quantity squared with the derivative of x sub I star, where x sub I star is that point where the slope of the tangent line is the slope of the secant line. And this now gives our expression for the hypotenuse as delta x times the radical 1 plus the derivative at that special value x sub I star quantity squared. Then we do what we always do. We take all of the segments and we add them up. Once we add them up, then we're going to take the limit as the number of cuts goes to infinity and the widths of our intervals go to 0. This leads to the definite integral from a to b of the radical 1 plus the derivative, quantity squared, times the differential dx. Let's look at the theorem for the arc length of a function of x. Assuming that f is a smooth function, meaning it has continuous first derivatives over the interval from a to b, the arc length of the portion of the graph from the point a f of a to the point b f of b is given by the formula arc length equal to the integral from a to b of the radical of 1 plus f prime of x quantity squared dx. Requiring the function to be smooth means that the first derivative is also continuous, and that means that we can definitely evaluate the integral. Let's take a look now at example 1. Let f of x be given by 4/3 times the curve x to the 3/2. Calculate the arc length of the graph of f of x over the interval from 0 to 1, and round the answer to 3 decimal places. You'll see here in the graph that this is the curve 4/3 times x to the 3 halves. We have highlighted the part between 0 and 1 in blue. This is the section whose arc length we're trying to find. It is a curve and not a straight line segment. You can see it most especially when it gets close to the origin. In order to do this, what we first want to write down is our formula. Don't forget that the formula is the integral from a to b of 1 plus f prime of x quantity squared dx. Let's write that down now. In order to compute the arc length of this curve over the interval from 0 to 1, we need to find the value of the derivative, square it, then add 1 to it, then evaluate the integral with that expression under the radical. Pause the video here, work out the mathematics in the calculus, then turn the video back on to compare your answer to mine. To find the arc length, we first need to compute the derivative by applying the power rule. This brings the 3 halves to the front to multiply by the 4/3, and we subtract 1 from the power. This gives us 2x to the 1/2, which becomes 2 times the square root of x. Then we need to square this, which gives us 4x. The expression that goes under the radical is 1 plus the derivative squared, which becomes 1 plus 4x. Now we put it into the integral itself. This brings us to the integral from 0 to 1. Notice the limits of integration match the interval over which we're trying to find the arc length. Then we have the integral of 1 plus 4x dx. We can do a u substitution as seen here at the right in green. Once we've completed the u substitution, we come up with this final answer, which is about 1.697. Refer back to the graph to be sure that you agree that that does seem to be a reasonable value. Since the length from here to here is 1, it does appear that that value is roughly correct. Let's take a look now at example 2, f of x equal x squared minus 2. We want to calculate the arc length over the interval from -2 to 3. You see here on the left the graph of x squared minus 2. That means the vertex has been pulled down 2. You can see in blue the region between -2 and 3, which is the arc length we're trying to find. This is a more difficult problem, so I've included the solution to it in the notes. Remember that our integral is going to be the integral from a to b of the square root of 1 plus the derivative value squared, and with the differential of dx. What we need to find first is the derivative. The derivative of x squared minus 2 is 2x. When we square it, we get 4x squared, and then we add 1 to get the expression underneath the radical. When we look at the next part, this becomes a trig substitution problem. I know you're not too happy about that, but this is a good review of all the techniques that we've learned this semester. Remember that we take the square root of the variable thing squared, which becomes 2x. Because it is added, it becomes tangent of theta. The constant 1 means it becomes 1 tangent of theta. The square root of 1, of course, gives us the 1. This means that when we try to rebuild what's under the radical, 1 plus 4x squared, we get 1 plus, and we square both sides to get tangent squared, which of course gives us the Pythagorean identity secant squared. Then we can replace the 1 plus 4x squared with secant squared. The next thing we need to do is we need to solve for x so we can replace the differential dx. We divide both sides by 2 to get x as 1/2 tangent of theta. Then taking the derivative of each side, we get dx should be replaced with 1/2 secant squared of theta d theta. Replacing this into the integral, we get the expression you see here. Note that the limits of integration have now been written x equal -2 and x equal 3 to distinguish that these are x values and not theta values because our differential has switched from dx to d theta. The square root of secant squared is the absolute value of secant of theta, but because of the nature of the angle, we do not need to worry about any of the absolute values unless we have tangent. That means that we end up with 1/2 secant cubed of theta d theta, which brings up, yep, you got it, integration by parts. I told you we're going to review most of the major techniques. Now we do integration by parts. Pull off 2 of the secants to serve as dv. So dv is secant squared of theta d theta, and when you integrate both sides, you get v is tangent of theta. That leaves 1/2 secant theta to become u. When we take the derivative, we get 1/2 secant theta tangent theta d theta. Applying the formula uv minus the integral of v du, or the tabular method, brings us to 1/2 secant theta tangent theta, evaluated between the limits of integration for x, minus the integral of 1/2 secant theta tangent squared of theta d theta. Now we want to make a substitution. This integral that we got coming out of the second part of integration by parts is now a trig integral. So we substitute tangent squared of theta equal to secant squared minus 1. And we replace it here in the integral. This part will not change and will hang out until we're ready to be done with this part right here. Note that what we're trying to find is the integral of 1/2 secant cubed of theta d theta. By replacing that value in here, we end up with this expression here, that 1/2 secant cubed of theta is equal to 1/2 secant theta tangent theta between the x limits of integration minus 1/2 secant cubed theta minus secant theta d theta. When we distribute, notice that we get another secant cubed of theta, which can be added to the 1/2 secant cubed theta on the left. This is a typical trig integral. When we move it to the other side of the equation, that gives us secant cubed of theta d theta equal to 1/2 secant theta tangent theta between the x limits of integration, and we can now plug in the values. It also gives us this 1/2 secant of theta, which we have memorized, or you can apply the trick of multiplying by secant theta tangent theta over itself, secant theta plus tangent theta. Bringing up finally, we come to this point right here. Now, of course, remember that what we're really trying to find is 1/2 secant cubed of theta. That was our original here. And what we now have is 1 secant cubed of theta. So when we're done finding our solutions, we'll need to multiply them by 1/2. Since we now have reached the point where we're ready to plug in limits of integration, we need to get rid of the theta and get back to x values so that we can replace them. That means that we need to undo that trig substitution that we started with by drawing the triangle. Remember that our original home base statement was 2x equals tangent of theta. That makes the opposite side 2x and the adjacent side 1. That means that the hypotenuse is 1 plus 4x squared. Then we can express the secant of theta as 1 plus 4x squared under the radical over 1, and the tangent of theta as 2x. That brings this expression right here for this first term, and this expression here for the second term. Since we now have x values inside of our expressions, and since the limits of integration are express values, x values, then we can substitute. Remember, however, that we needed 1/2 secant cubed of theta, so we will need to multiply these 1/2s by another 1/2, and that makes them 1/4. This is the final value that we get for our arc length. In other words, it's roughly about 14.4 units long. Let's look back at our picture and see if we buy that answer and if that answer looks reasonable based on the picture that we have. Looking at the picture where this is a distance of 1, do you buy that the distance from here around to here is roughly 14.4? It sounds about right to me. Let's take a look at another example. This is a really interesting curve. the function x to the fourth divided by 4 plus 1 over 8x squared. It gives this weird sort of U behavior that you see here, but of course it's not defined when x equals 0 because of the second term. We want to find the arc length over the interval from 1 to 3. That's the blue section that you see here on the curve. It looks relatively long, seeing that this is a height of 20 and a distance of 1 is this small measure right here that you see on the x-axis. It looks relatively long. In order to compute the arc length, we need to find the first derivative, square the derivative, add 1 to it, and then place it under the radical and compute the integral from 1 to 3. Pause the video here and then restart the video to compare your answer to mine. In solving this problem, you'll note that the first thing I did was to rewrite 1 divided by the quantity 8x squared in power form as 1/8 times x to the negative 2. Then I applied the derivative to come up with x cubed minus 1 divided by quantity 4x cubed. The next thing I did was I squared that. You'll want to be very careful when you're doing the squaring. I recommend that you write it out twice and very carefully apply the technique of FOIL or the distributive property to find it. When you're doing this, note that you get a minus 1/2 in the middle. This minus 1/2 is crucial to applying the formula for arc length. It becomes a part of the pattern. What you're going to find when you add 1 to it is that the minus 1/2 becomes a plus 1/2. That means that essentially this is the same perfect square trinomial, but instead of a minus 1/2 in the middle, it becomes a plus 1/2, which means that it refactors as almost the same binomial squared, but with a plus sign in the middle instead of a minus. That pattern is the only way to get these to work. So when you see that minus 1/2 pop up, note that when you add the 1 to it from the formula, it becomes a plus 1/2, so you get exactly the same binomial you started with, but with a plus sign in the middle instead of the minus sign that you had to start. Look for that each time. Once you know that this is the plus, then you can replace what's under the radical with that binomial type thing being squared. It's not a true binomial because a true binomial would not allow the variable in the denominator with a positive power. However, it is binomial-like. When we have the square root of something squared, we would normally get absolute value, but in this case we can ignore the absolute values. Why can we ignore the absolute values? Think for a moment about what the limits of integration are. They're going between 1 and 3. That means because they're going between 1 and 3, and I'm not sure why there's an x there, because they're going from 1 to 3, my x values are strictly positive. If the x values are strictly positive, then what's under the radical is strictly positive, and therefore we can ignore the absolute values. This gives us this expression here after we've evaluated the integration, and working out the arithmetic brings us to the value of about 20.1, repeating. This makes sense and looks correct when compared to the original picture. Let's take a look now at example 4, and after that we'll do an arc length of a curve as a function of y instead of as a function of x. In example 4, we have the curve, the natural log of quantity sine of x, and we want to evaluate the arc length between pi over 6 and pi over 3. Now, between pi over 6 and pi over 3 is a relatively small range, given that pi is about 3.14. This is only going up to about 1. That means that I've got a relatively small region, so I'm expecting my arc length to be quite small. When you graph the picture, you can see that it shows up right here, and the region we're looking at is this tiny little section in blue. Let's now take a look and see what we get when we apply the formula. Remember that the formula that we have each time is the integral from a to b of the square root of 1 plus the quantity f prime of x squared with the differential of dx. In a moment, we'll take a look at doing some with respect to y. Pause the video here, Compute your calculus and then turn the video back on to compare your answer to mine. Recall that the derivative of natural log is 1 over u du dx. Remember that you have to invoke the chain rule because you have a composed function. This gives us 1 over u times the derivative of u, which is sine of x, and the derivative is cosine of x. This gives us cosine of x over sine x, or cotangent of x. When we square it, we get cotangent squared, and when we add 1 to it, we get 1 plus cotangent squared, which is a Pythagorean identity of cosecant squared. Now we can place the cosecant squared under the radical and evaluate the radical. Why do we have no absolute values? Again, consider what the limits of integration are. We're between pi over 6 and pi over 3, which means that we're remaining in quadrant 1. Because we're in quadrant 1, all 6 trig functions, including cosecant of x, have strictly positive values. This is a trig integral. I know, you're dying. Hang in there. Remember the trick of multiplying by cosecant of x plus cotangent of x, very similar to the secant trick that we talked about earlier. Now we set u to be the denominator, cosecant of x plus cotangent of x. We distribute the cosecant of x in the numerator to get cosecant squared of x plus cosecant of x cotangent of x when it's distributed. Note that when we take the derivative, we have a negative which we can factor out. That means that the numerator becomes a part of du with the negative along. Then we can make the substitution. Notice that we have a negative here, and I dealt with the negative by switching the limits of integration. Then I can evaluate it, and I can replace the u again with cosecant of x plus cotangent of x and plug in the limits of integration. When I did that, notice that I got 3 over the square root of 3, which reduces to square root of 3. Our exact answer is the natural log of 2 plus the square root of 3 minus the natural log of the square root of 3, which of course could be written in a combined form of the natural log of 2 plus the square root of 3 divided by square root of 3, which of course can be simplified further into the natural log of 2 divided by the square root of 3 plus 1. There are lots of forms to write the correct answer. It comes out to be approximately 0.768, which does coincide with what we thought about the length. Now let's take a look at the next section, which is arc length of a curve as a function of y. Sometimes a function is better expressed as a function of y instead of as a function of x, particularly if it has a point where the tangent line goes vertical. The formula is very, very similar. In this case, the formula is let g of y be a smooth function over the interval from c to d. Then the arc length of the portion of the graph from cg of c to the point dg of d is given by this integral here. Let's take a look at an example. In example 5, we want to find the arc length of the curve given by x equal 1/3 of the quantity y squared plus 2 raised to the 3/2. Yes, we could go through and try to solve it for y, but because of the y squared, we'd end up with plus or minus a radical. In this case, it's easier just to leave it as a function of y being solved for x. We want to find the region between y equals 0 and y equal 1, which corresponds to the blue shaded region here. Notice that our limits of integration and our interval are given in terms of y and not in terms of x. The formula, however, is very similar. The formula is essentially the same. Find the derivative, but this time the derivative with respect to y, square it, add 1, place it under the radical, and evaluate the integral. Go ahead and pause the video here, work out the algebra and the calculus, then turn the video back on to compare your answer to mine. Note that we have to apply the chain rule and the power rule here. The 3/2 comes to the front and multiplies by the 1/3, and we reduce the power by 1. Then we have to take the derivative of the inside function, y squared plus 2, and multiply by its derivative, 2y. Simplifying, we get y times the quantity y squared plus 2. Now we take this and we square it, which gives us y squared times the quantity y squared plus 2, or y to the 4th plus 2y squared. Then we add 1 to it to obtain the polynomial y to the 4th plus 2y squared plus 1. We're going to take this and put it underneath the radical. When we put it under the radical, remember that we will need to factor it or do something to it so we can take the square root of it. In this case, it does factor directly as a binomial being squared. The square root of a binomial squared normally gives you absolute value, but we can drop them. No, it's not because we're between 0 and 1. In this case, it's because y squared plus 1 can't possibly be negative. Y squared is always positive, and adding a positive makes it still positive. But you could also say it's because we're between 0 and 1, so the y values are positive. In any case, we can drop those absolute values, and then we can evaluate the integration very simply to get 4/3. Does this jibe with what our picture looked like? Since 4/3 is basically 1 1/3, and this distance right here is a distance of 1, I can buy that this distance from here along the curved edge is about 4/3. It does seem to make sense. Let's take a look now at our last example in this video, example 6. In example 6, we again want to find part of the arc length of a sideways parabola, this time given by x equal 4 times the quantity 3 plus y squared. Notice the scale here is huge. This is going out on the x-axis out to about 200, but the y scale is very small, only between -10 and 5. We want to find the arc length for the curve between y equal 1 and y equal 4, which is the blue shaded region you see here. Remember what our formula is going to be. Since we're going with respect to y now, we'll go between c and d of the radical of 1 plus the function g prime of y, quantity squared, with the differential of dy. Go ahead and pause the video, work out the algebra and the calculus, then turn the video back on to compare your answer to mine. First, we start by finding the derivative with respect to y. This also invokes the chain rule, where we bring the power 2 to the front to multiply by the 4, leave this alone and reduce the power by 1. Then we take the derivative of the inside, 3 plus y, to get 1. This gives us 8 times the quantity 3 plus y. Next, we square this, which will give us 8 squared times 3 plus y, the quantity squared. I should really have a 2 on the 8 as well. Then we add 1 to this. This gives us 1 plus 64 times the quantity 3 plus y, quantity squared. We put this underneath the radical, and then we have to evaluate. This is going to give us another trig substitution problem. In our trig substitution problem, we have the constant of 1 here being added to a variable thing being squared. That's going to be a substitution factor of tangent. Because we have a 1 here, it becomes 1 tangent of theta. Then we take the square root of the variable thing part, and we have the square root of 64 is 8, and the square root of this part gives us 3 plus y. So 8 times 3 plus y is equal to 1 tangent of theta. Then we rebuild what's under the radical by squaring both sides of the equation and adding 1. This will lead us to secant squared of theta. Then we have to replace the differential dy. At the moment, we have 8 times 3 plus y equal tangent of theta, so we solve for y to get 1/8 tangent of theta minus 3. Then we take the derivative of both sides to get dy equal to 1/8 secant squared of theta d theta. This will replace the dy in the integral. Once we've reached that point, we have the radical of secant squared of theta times 1/8 secant squared of theta d theta. Recall that the only trig substitution where you have to worry about the absolute value is when you have tangent left up underneath the radical. Since we have secant squared, we will not have to worry about it based on our definition of theta. This gives us 1/8 secant cubed of theta d theta. We've already done the integration by parts on this once in this particular video, so we'll skip that and go right ahead to the solution. This gives us 1/16 tangent of theta secant of theta plus natural log secant of theta plus tangent of theta, evaluated between 1 and 4 for the y values. Since the limits of integration are y values, but the variable inside the expression are theta values, we need to use our trig substitution factor in order to go back and use the triangle to get back to y. Our home base equation was 8 times 3 plus y equal tangent of theta. That makes the opposite side 8 times 3 plus y, adjacent side 1. By squaring these two and adding them together, we get the hypotenuse here, which matches what we originally had under the radical. Then we can replace tangent of theta with 8 times 3 plus y, and secant of theta with this radical that we see here. Replacing those inside the expression and then plugging in the limits of integration 1 to 4 leads us to a very long and complicated exact solution and the approximate solution of 132.035. Based on the scale that we saw in our original picture, this does seem to make sense. This is the end of this video on arc length. In the next video, we'll be discussing surface area. The surface area formula will use the arc length formula, so be sure you understand arc length before beginning surface area.